Okay, I just started recording. Hello, class. Today we start with chapter 8. The first 3 sections, I don't think we'll get to the induction today, on sequences, summations, recurrence relations. Okay, let's go to it. So first, what is a sequence? A sequence is a special case of a function where the domain of the function is a range of consecutive integers. So look, for example, here. Let's define a sequence as the height of someone rounded 2 inches on each birthday from this person, from the beginning to the 5th birthday. Okay, so that's a sequence of 6 numbers, right? This is how many inches they got on day 0. This is how many inches they had when they were 1 year old, 2 year old, 3 year old, 4 year old, 5 year old, etc. Right? So this is my this full sequence because I just care about the first 6 birthdays, including the 0 birthday, right? The birth itself. You can look. So this is a function from the domain of 6 consecutive integers. Okay, so this is an example of such a domain. 2, this happens to be in integers, right? Because I said that I'm expressing height in inches, exact inches, so these will be integers. But this part is arbitrary. This is just an example. I can have a sequence of other objects, like, for example, rationals, or somebody asks if the slides are posted. Posted will be after lecture. All right. So, okay, but the domain being consecutive set of integers, that's always the case. So that's the way to define a sequence. Alternatively, you can think of a sequence as a 6 tuple of integers, right? So that was from Tuesday. We define a Cartesian product of integers 6 times. These are 6 tuples of integers, right? So this is also a convenient notation for a sequence of finite length. And these two are 1-to-1, right? So whenever you have an object like that, which is a function, you also have an object like this, a tuple, all right? And you can go between one representation to another easily. Okay, so this is a finite sequence, right? A map from 6, here's the example, 6 consecutive integers to integer values, because these were inches rounded. But you could also define a sequence on infinite domain. So let's look at an example. It's a sequence. The first element in the sequence is 1, the second is 2, the third is 4, 8, 16, 32. It's a exponentially growing sequence, right? Oh, no, geometrically growing. No, exponentially, yes. And that sequence is a function from all positive integers, right? Because I have the ... which basically means that this is an infinite sequence. Okay. And now, how do you know what the next values of the sequence are? I haven't specified them. Well, you do it by pattern matching. So you realize that what the sequence is every next guy is twice the previous one, right? 4 is twice 2, 8 is twice 4, 16 is twice 8, 32 is twice 16, and then you can basically derive the sequence on your own. Okay, so this is the same as in set notation, that, well, I can define a set in this way, as long as every mathematically literate person will be able to read this, right, and decipher. I mean, basically recognizes what's the rule, what's the sequence really here. Okay. So, and the infinite part is that the domain is all positive integers, right? I start with with number 1, then 2, then 3, 4, 5, 6, and all integers, right? Okay. Now, the indexes in the sequence can be just have to be consecutive integers, but the initial one can be anything. Okay, so it is just customary to define sequences either like this, start with h0, or like this, start with think of the first guy as index 0, or think of the first guy as index 1. Even this is just a convention. So you could define a sequence. You can start from -2 if you so please, okay? Or you can start with the index 100. It will define a fine sequence, right? It's just that it will be a little harder to read. So these are the natural ones. And you can do this or you can do that. We don't care. You should be able to read either one, or indeed you should be able to start at any index, okay? Because if your sequence is of the number of driving licenses given to different age groups, well, you can call the first element of this sequence not call it index 1, but call it index 18, or whenever it is that Americans get their driving licenses first, right? Okay, so you can specify sequences like a set, like explicit set constructor. Just list them. Okay, so these are of course best or good for finite sequences, especially, right? Average rainfall in California since 1950. Okay, so that sequence will have 71 elements, right, from 1950 to 2020. And you just have to list them, right? Because I don't think it obeys any law that can, describe this sequence in a more concise way. Weight of average people by age. Okay, so that will be a sequence with, sadly, I don't know what's the oldest age of an oldest person on Earth. Is it 120 or more? But it's about that. That's how many elements that sequence would have. Or you can give an explicit formula. So for example, you can define a sequence, excuse me, a sequence, call it, and by the way, this name H for sequence, that's arbitrary. You can use any variable as long as you index it, right, with some indices, and these indices have to be consecutive integers. So here is an example when I call my sequence F. Elements in the sequence are called Fs, and this is the nth definition of the nth element of the sequence. So, so for every n, Fn is this expression. So actually, I could rewrite this as a function. Just call it F brackets n, right? And then you have the explicit functional notation, which treats, which just reminds you that the function, that a sequence is a function whose domain are consecutive integers. Okay, and now where does this sequence start? Okay, I have to say which is the first one. So let's say initial index is 1. Okay, so this sequence will be the first element in the sequence. I put 1 here, and then I read off what this formula defines. So it's 2 to the 1 plus 2 times 1. So it's 2 plus 2, 4. F2, I put n equal 2 in this formula. So it's 2 to the second power plus 2 times 2. So that's 4 plus 4, 8. Look at F3. So this is 2 to the third, which is 8, plus 2 times 3, which is 6. So it's 8 plus 6, 14, and so forth. Okay? All right. So you can have infinite sequences defined by explicit formulas. For example, a sequence H, okay, is defined, the first element in the sequence, the first index would be 1, right? Because that's the first element of positive integers. And I define this sequence as basically an identity. So the nth element in the sequence is just n itself. The sequence, if I want to express it, so that's another notation for a sequence I'm introducing here. I'm calling this infinite tuple with the same variable that I used to define a function. Because indeed, this infinite tuple defines a function where the understanding is that this is the value the function takes on argument 1, this is the value the function takes on argument 2, etc. And this sequence defines an identity function, right? So when looked at using sequence notation, this is H first, this is H2, this is H3, etc. Okay, let's look at more maybe an example where the function is not an identity and therefore it's not possible to confuse indices from the actual values of the sequence. So look at sequence G, defined over positive integers. So the first index is 1, and the set of indices is infinite. So it's an infinite sequence, starting at 1, defined that at ith position, the value is 2 divided by I. Okay, that's a real number. Actually, it's a rational number, right? So it's in particular, it's a real number. So what are these? So the first element, G1, is 2 divided by 1. So the first element is 2. The second is 2 divided by 2, right? Because the index of this element is 2. So when you evaluate this function at index 2, x equal 2, you get a 1. At index 3, you evaluate this function for x equals 3. That's here. This is 2/4, which simplifies to 1 half, 2/5, 2/6, 2/7, 2/8, and so forth, right? Or you can have a constant function. I call this sequence with I, okay, and at every index, the value of the sequence, the element in that sequence is equal to 3, okay, because the sequence is defined through a constant function. Sequences can range over many sets. You can have a sequence of real numbers. You can have a sequence of integers, sequence of bits, and so forth. Okay. Now, instead of so you have seen examples of an explicit formula. We're going to call it a closed formula because it's some function that you can evaluate knowing just the argument. Now, that's not the only way you can define a function, although it seems like that should be the only way, but it's not. Okay, you can define functions and sequences through recurrence, well, because sequences are functions, through recurrence relation. You have to define two things. First, a base case, which is what are the values of this sequence at few initial indices. So here you have an example when I explicitly define what's the f0th element. So I start this sequence at index 0, at 0th and at first, and I'm declaring them both to be equal to 1. And then I have a recursive rule, which is the second part of the definition. And that's a rule which defines next element in the sequence using some formula, some function of previous elements that involve previous elements in the sequence. Some number of them, perhaps here is an example where you define nth element of the sequence in terms of previous 2. Okay, And for this to be a complete definition, you have to make sure that those two combined define the function for all integers, right? Because that's the only way you can make it a definition of an infinite sequence that starts at index 0.
Is a Fibonacci sequence an example of a recurrence relation?
Yeah, this is a Fibonacci sequence, exactly. Yes, right, good point. This is a Fibonacci sequence. So you define the nth guy as a sum of the previous two, and you declare this holds for indices greater or equal to 2. So what's the first guy that is not defined through the explicit formula? Well, it's f2. Now I can use this formula to define f2, because f2 is going to be the sum of f1. Here is 2 minus 1, so that will be f1. And here is 2 minus 2, that's f0. That's f0. Let's do this on the next page. So here is the same, and indeed it's a Fibonacci sequence defined through this base case and the recursive rule. Let's see how to evaluate this. Okay, so for n equal 2, this formula reads f2 is f1 plus f0, right? This is this formula for n equal 2. And here I have it written. And now I just substitute, because I'm lucky. f1 and f2 are both defined by the base case. They're both 1. So it turns out that f2 is 2. Let's do it in the next one, n equals 3. For n equals 3, if I instantiate this recursive rule for n equals 3, I get this equation. f3 is the sum of f2 plus f1. And then I read off, because f2 was already evaluated, and f1 was also declared. So I know that these guys are 1 plus 2, 3. And I can continue, right? The fourth is the sum of the third and the second. And note that at every point, all the previous ones are already computed. So zeros and first are declared, and I computed the value of the sequence at second and third index. And the fourth will be these two summed, so it's 5. The fifth would be f4, f3, so these two summed, it's 8, and so forth. The next one is the sum of the previous two. The next one is the sum of the previous two, and so forth. All right? So that's how you evaluate it. And why did it work, right? So it is, well, you see intuitively that you can do this to any number, right? So if you want to, you can evaluate the 100th element of the sequence, the 1000th element of the sequence. It will take you quite a lot of computation, right? Computing nth element is linear in n. So it's going to be n operations, n additions. That's not particularly efficient if you are curious about what the sequence is for large n, right? But it is possible. And intuitively, why it's possible? Well, we later will prove this by induction, that this works. Also, it's, it's kind of obvious that it does, right? Because what's the intuition? That, well, it works for the first two, they're declared. Their values are declared. And then, look, whenever the function is defined for some two, then it's also defined for the next one. And that's will be the principle of induction, because that means that it's defined for the next one. And also, if you take these two, then the next iteration of the same rule for n1 incremented will define fn plus 1, fn plus 2, and so on. And therefore, it will define it for our integers. Okay, another recurrence relation. So let's declare G0 to be 0 and Gn to be G at an index given by n div 2. And then I take that element in the sequence and I add 1 to it. And that's a recursive rule. This is the base case. This is a recursive rule that works for all integers greater than 0. Okay, what is n div 2? That's the floor of half n. Okay, so what's the floor? It's rounding to the nearest integer down, right? So if this is an integer, floor just gives you this integer. And what's the other possibility? Is that this thing is integer plus half. in which case this becomes that integer, whatever that is. Okay, let's see how that works. So for n equal 1, G1 is n1 div 2. What's 1 div 2? That's 1/2, and the floor of 1/2 is 0. So this is G0 plus 1. Okay, let's do G2. G2 is G of 2 div 2. 2 div 2 is 2 divided by 2 floors. So this is 1 floor, this is 1. So G2 is G1 plus 1. Okay, boom. Okay, G3 is G3 is, somebody asked me on the chat if I can hear their mic. I can't, so it's all good. So G3, okay, let's look. 3 divided by 2 floor. So this is 3 halves. That's 1.5 floor, 1. So that's why this thing for n equal 3 is just 1 plus 1. All right. What the next two? Okay, because basically we can notice that like this function is always, this guy will be the same as this guy. Why? Because 5 div 2 is the same as 4 div 2, right? Because this is 2.5 and this is 2. So the floor is the same, right? So they both are defined, these two, in terms of G2, just like these two were defined in terms of G1. So it is defined in terms of G2 plus 1. So, okay. And now, look, G6, what's 6 div 2? That's 3. So these, both of them will be defined in terms of G3. But G3 was the same as G2. Therefore, this pair is the same as this pair. These two are the same as these two just because G2 was the same as G3. So if you see, like, if you continue this sequence down, you will see that the next chunk of values will be 4s, and 8 of them will be, because this whole chunk will map to a, one chunk of 4 elements, and then it will map to another chunk of 4 elements, and then so there will be 8 4s, and then what's the next? It's 16 5s, and then 32 6, and then, all right. So what is it? It's a logarithmic sequence. Okay, this sequence, if you wanted to describe it in a closed formula, you would say that Gn is the logarithm base 2 of n with the proper rounding, right? So you have to put a floor. All right, but it basically grows like logarithm. And you might not observe this first, So look, such a simple thing. And what you get is a definition of a logarithm in some sense, right? Or at least rounded. And where do you see logarithm here? Well, you kind of do. Because if you think of this, that's logarithm. Logarithm function is the one whose value at some point is 1 plus the value of half that point. Okay? That's how logarithm acts. So, and yeah. Okay, but it's a different view of a logarithm function, right? It's like a functional view, like computational view in a sense. So these recursive definitions, these are recursive definitions for sequences. They're basically like a little piece of recursive code, right? You define, if you wanted to compute what the Gn is, this code would be suffice, because you'll be, okay, what's at n? Okay, it's at half the n plus 1. And now recursively, what is it for half the n? Okay, I stick this, and that's now for n divided by 4. And what is it for n divided by 4? Well, it's whatever it was at n divided by 8. And I plus 1 every time I do the recursive call. At some point, I hit the base case. This is 0. And then the whole thing evaluates. It's just you accumulate these plus, plus, plus ones. And how many times do you accumulate? Well, as many as this thing was the power of 2, because at every power of 2 you added a 1, right? So that's why it's a logarithm. But basically these pieces are like little codes, right? A one-to-one to an algorithm that actually computes something. Okay, another recurrence relation. Base case is now defined by two values, and a recursive rule is here. Okay, so I call that sequence H, that's arbitrary. I start with an index 0, that's arbitrary. Okay, so I define the first two as 0, 2, and 4. And then I have a recursive rule that defines the next element in the sequence as nth element as some formula that uses previous two, but it also uses the index itself. Okay, that's still a recursive formula. That's still a recurrence rule. Okay, so the recurrence rule can have n inside of it somehow, and like for example here it does. And this I define for n greater or equal to 2. So the first guy not defined is h2, but that's index n equal 2. So hopefully I can use this formula, and yes, I can. Okay, so I need to make sure that the number of initial values suffices for whatever recurrence rule is to define this sequence everywhere. So basically you have to look, okay, this sequence is defined in terms of how many previous ones? 2. Okay, I have to have 2 base cases. But look, this is not exactly an automaton, okay? Because this guy is not defined as a previous in terms of a previous. It's defined as an element of the sequence that was before, but was way before. Okay, if this is 1,000, then this is 500. All right.
So would we call that? Would we call that if we were doing in terms of, let's say, like k plus 1? Would it be like k plus 1 divided by 2 if k is an integer? Does that make sense?
Hey, where do you see k here?
No, I'm just making up like a random, like a variable name.
Then I don't know what you're saying.
Oh, like when you're talking about the previous sequence, like in like n divided by 2, would you define that as for some n divided by 2, like something further up ahead exists as well? If we're trying to prove recurrence?
You know what? No, so you okay. Look, you can complicate it a lot. Let's just look at some examples. Okay, I just give you some examples. Like sometimes
Okay.
it will work, sometimes it will not work. If this is very complicated, how you go from one index to another, you know, I can. I'm sorry, you have to write this for me to tell. Like, is that good or is that gonna have a problem?
Okay.
Most of the time, it's gonna be, you know, simple. As in, the next guy is defined as some formula involving some number of previous ones. So here, since I'm defining n's as in terms of the previous two, just like in the Fibonacci sequence, but it is not a Fibonacci sequence because there is this modifier here, right? The first two suffice to define the rest. So for n equal to, what is h2? That's 2h1 plus h0. That's this formula, right? And since I know what h0 is and what h1 are, I just put them in and I evaluate. N equals 3. What's this formula? That's 3 times h2 plus h1, because n is 3. That's this formula. Okay, and since I have basically the invariant that every time I compute the next, all my previous ones are computed. Zeros first, second. So whatever this thing was, I know how to read off these values. So I just stick them in and compute. For n equal 4, what's this formula? It's 4 times h, 4 minus 1, h3, plus h, 4 minus 2, h2. Right, and I evaluate, and so forth. So as you can see, of course, you know, if Fibonacci is defined as the sum of previous two, and this sequence is defined as, well, take the previous two, but multiply the one before by the index of the sequence. So this is going to grow way faster than Fibonacci, right? It's like a Fibonacci, you know, extra. Let's look at this recurrence relation. It's also a good recurrence relation, okay? It defines a value of the sequence at index j plus 1 in terms of 3 sequence elements. The sequence element at index j, sequence element at index j minus 1, and a sequence element times j minus 2, excuse me, and then it applies some algebraic formula to them, right? Takes this once, takes this guy twice, and adds, but then subtracts 3 times this. So how many initial values do you need for this to successfully define an infinite sequence? Well, you need 3 consecutive elements, right? Because if you just start with, like, let's say that only h0 is given, could you use this formula to define what h1 is? Okay, let's try. How could this define h1? Well, that would be for j equals 0. Okay, so h0 exists, but h minus 1 does not. We only declared h0 to be something, right? So we need to extend our base case. Let's think h0 and h1. So who is next? It's h2. So let's try to use this formula to compute h2. That's j equal 1. So this is h1 defined, good. This is j minus 1, so this is h0 defined. But this guy will be undefined because this index will be minus 1. So you can see that if I declare the first 3, I'll be fine, right? So you need 3 initial values at any places. So they could be perversely defined at index minus 10, minus 9, and minus 8. And this formula for j greater than minus 8 will define, or minus 7, yeah, at least minus 8, right? Will define this. Will define all the next ones. Okay, so the initial point does not matter where it is. It's going to define, as long as you define 3 consecutive ones, this thing will define for every point afterwards. Okay, so it is, let's say, h0 is 0, h1 is 3, h2 is 5. This will successfully define all the next. Okay, so let's test. J equals, so how do I define h3? This index has to be 3. So that's the case of j is equal to 0. So h3, and then I read off the formula instantiated with j equals 2. So this is h2 plus 2h1 minus 3h0. That's this, right? And because I have some values for these 3 consecutive ones, all of them, I just stick it in and compute. J equals 3. So this is h4, this is 4, h3 plus 2h2 minus 3h1, this one. Okay. Okay. And so on, you can evaluate now, right? Somebody asked the number of terms required in whatever n you need such that all indices are greater than 0. Oh, sorry, I cannot parse your question so quick. Sorry, but everybody here sees it, so maybe someone can respond. Recurrence is so okay. Where do these recurrence relations come from? So these are basically dynamic systems. Like for an nth instance of the system's parameters are function of previous values of some parameters in the system. So that's that's in biology, in well, I guess even in chemistry, but in finance, in all sort of sociology, economics, network behavior. Well, right now, sadly, the virus and right, like spread of disease can be also modeled as a dynamic system like this, right? Useful. So in computer science, as I was saying, these are basically recursive algorithms. Okay, so they will capture very well what an recursive algorithm does, and there is more cases where this comes in. So let's do an explicit example of some recursive algorithm. So here's merge sort. Okay, so here is merge sort L, the input of a sorting algorithm is a list. Okay, so a finite sequence of, let's say, integers or any values that you can compare. That are bound with some greater or equal relation, right? You can also sort alphanumeric strings, like names. Okay, the base case of the algorithm is that if the list is empty or it contains only one element, then you don't do anything. You just return the list. It's already sorted. But if it has more elements than none or one, what do? You divide it into half, left half and right half. And if it's not even length, then you just make it one of them greater than the other by one. You recursively apply the same merge sort algorithm to both the left half of the list and the right half of the list. So whatever the list is, you just split it into two and run the algorithm recursively on the results. Now, assuming that the algorithm is correct, you can assume, okay, therefore these recursive calls will come up with a sorting. So A will contain all elements in here, but sorted. And B will contain all elements in here, but sorted. So whatever my elements were, now I have two sorted lists. So what does this final call do? It merges in order. So no, look, this is easy. If you have two sorted lists, you can put them along like this. And then you start on the left. And what you have to do is just compare the first guy in both lists and put them in a proper order, either this way or that way. And then you increase the index. And then you increase the index only on one list, right? So you just compare them side by side and progress. How many comparisons you have made? Linear, because every time you make progress, you increment one of these indices. And therefore, you have to finish. By the time you are done, how many comparisons you have done? For every comparison, you increment. So if the list was length n, then this whole thing runs in time n. So that's the beauty of merge sort. So let's express as a function. Okay, and that's a function or a sequence, right? Because the domain is integers. F of n is the running time of this algorithm if L is an n element, contains n elements. Okay, and I'm going to ignore all sorts of stuff when computing the running time. I'm just going to compute number of pairwise comparisons. So let's say all the other data structure stuff, jumping and so forth, this costs me nothing. The important part is comparing. Okay, that's the costly operation. All right. So they're bound by so basically we can read off from this algorithm what is the formula for f, and it's going to be a recursive formula. Look at the base case first. If the list has one element, then the running time is 0. I perform no comparisons. So hence then I could add a base case f of 0 also, right, to be complete. It will also be equal to 0. Now for all greater integers than 1, f of n will be however many comparisons this algorithm did. Well, but that's my algorithm. So the running time is f of the length of this. But the length of this, let's say I always make this longer if I have an odd split. So this is the ceiling of n divided by 2. And this, the number of elements here, will be the floor of n divided by 2. And how many comparisons I do at the end? Well, it's actually not n, it's n minus 1, if you want to be exact. So that's the formula. And look, it's a recursive formula. I have a base case, or base cases, because probably I should add here f of 0 equals to 0, 2. And I have a recursive case. Recursive definition, which is the recurrence relation. And I define nth in terms of not the previous one, one basically roughly half the size. We're not going to derive this formula, explicitly now. I'm just going to observe that a close enough approximation to this. Just think of n being a power of 2, just to simplify life. All the other ones will be in between these cases, so this is a good approximation. So basically what this formula says is that f of n, it's f of n half plus f of n half, so it's 2 times f of n half. Okay, and let's just treat this thing as n. This is a simple recurrence relation. And look, we had a case of this. So this one indeed has this relation. So it's almost the same thing. If I ignore it, again, I can either put in the floor or ignore it, right? So if I ignore it, I will basically have almost this, except that there is I multiply by 2, and here I didn't, and I add. So note, remember, the closed formula for this recurrence relation was simply a logarithm. Okay, so this might not be exact. This might be plus minus some error. Okay, but it's roughly this. It's order of logarithm. The closed form of this formula. So when I have almost the same definition, except that this guy now is not just equal to this one. It's, oh, sorry, actually I have a typo here. The logarithm was, it was this plus 1. It was plus 1 here. I will copy this on the slide when I post them. That was the definition there, right? Otherwise it would be a constant function, but it had a plus 1, hence was logarithm. So it turns out that if you do this, the formula in the end is grows like n times log n. Okay, it will take us a while before we could derive such rules. It's not too long. But you have an example of a recurrence relation for something, of immediate use in computer science, right? A recursive algorithm, a famous one. So where did Fibonacci came up with this? So obviously he didn't think of recursive algorithms, data structures, right? He had a nice problem: population growth of colony of rabbits. The problem was like, oops. So he assumed that every pair of rabbits creates another pair, but only after they're older than 2 months. So a 1-month-old rabbit is too young to replicate, to have babies. But once they are older than 2 months, 2 months or more, they do. Okay. So if f expresses f of n is the population of rabbits at month n, so it's all the rabbits, though assume they don't die. They are all the ones you had, right? Because they remain. And then how many new ones do you get? Well, how many people are going to reproduce? And because every pair creates a pair, so they double. I mean, they add the same number as their multiplicity, right? However big cardinality of the set was, the new additions is that cardinality. So what's the population of rabbits 2 months ago that are at least 2 months old? Well, that's the population 2 months ago. So that's this. This is the amount of, this is the population 2 months ago. This is the populations that are at least 2 months old. This is the number of rabbits that you're gonna get in month n. So hence, that's how Fibonacci got. Apparently this formula, entered Indian mathematics earlier in some strange things that is mysterious to me. And if somebody understands how this came up exactly, a point I linked to on the Piazza. So you have this beautiful, concise, closed formula, recursive formula, but Now you would like to ask some questions like, how big is the colony after 100 months? Okay, I can take 100 operations to compute it recursively, but I would like some faster way. Or for example, I want to say, okay, what's the month until they get to 1,000? How long do I have to wait for that? Well, is there a way to compute this without evaluating one by one? It would be nice to have an explicit formula for it, or so-called closed formula for it. So that's called solving a recurrence. So you have a recurrence relation, which we had all these examples. It's defined by two things: base case or base cases, depending on your recursive rule, and the recursive rule. That these two have to cooperate. The recursive rule has to successfully define values for all cases after the base ones, and the base ones have to define sufficiently many for the recursive rule to be able to do that. And alternatively, explicit formula or closed formula is some expression, some definition of the same sequence, which makes no reference to other elements in the sequence, right? So I can evaluate f of n as a function that does not reference values of f anywhere, like say f of n minus 1, right? No, it does involve n, the index, but it's a closed formula in the sense that however big the formula is, I can stick n to it and then hopefully efficiently compute this expression, right? But it's not strictly speaking true that like whatever n is, this will get me constant time, because I don't really have constant time algorithms to compute exponentiation. But at least it's not linear in n. I don't have to compute this over and over for all the previous n's, right? I can just take however big my n is and stick it in here, and I don't care to compute this for all the previous n's. So geometry. So okay. So let's look at some famous sequences. Here is a geometric sequence. It's the initial value. It's defined through an initial value and through a recurrence relation that defines the next element in the sequence as a product of some fixed ratio times the previous element. So this is it's a sequence that, okay, the first element is A, the next one is A times R, the next one is whatever that was times R, the next one whatever that was times R, etc., right? So G first is R times A, G second is R times that, so it's R times RA, which is R square times A. The third is R times the previous. Well, the previous was R square A, so it's R times R square A. So it's R cube A, etc. Right? So basically you're going to have powers of R that will accumulate. And if you, you can basically read off. I mean, you can have a hypothesis for, okay, so it looks like the closed formula for this is that, okay, at any index, I will have, the formula will be R to that index times A. This seems to be true for even that guy, right? So this is n is 0, is R to the 0 is 1. Here is R to the 1, R to the 2, R to the 3, R to the 4, right? And using induction, indeed, you can prove that this is the correct formula for all n. It's the only formula that satisfies this recurrence relation. Okay. So you will see that's why the two topics are connected. So the induction is kind of like a flip of the recurrence relations. Is the whereas recurrence relation define something at any point, at infinite sequence of points. Induction is a way to argue about objects that are defined in such a way. And if you don't care about these infinite sequences, then but do care about algorithms, then you can say, oh, well, a recursive algorithm is just like a recurrence relation. It's an kind of an object that whose values are defined in terms of the values at smaller indices in some sense. And an induction will be a way to argue some properties of such objects. Like, for example, that the merge sort runs in exactly this time that we claimed, right? N log n. Or perhaps that merge sort always terminates, or perhaps that merge sort is actually correct, right? Which we would really would like to. I mean, it seems intuitively the case, but how about a proof that it is so, that no case is missed? So that would be the role of induction. Let's look at some geometric sequence examples, right? So this is the general blueprint for geometric sequence. So let's run it with the initial value 5 and a ratio 2. So this sequence will take 5 and multiply by 2, and then the next one by 2, the next one by 2. So this is the sequence you got, right? Like you start with 5 and you start multiplying by 2, by 2, by 2, by 2, by 2, by 2, right? In particular, you can see that it's strictly increasing. What if you multiply by your ratio is less than 1, right? So in this case, it's 1/10. So you start with something and you multiply by 1/10, and then you take the result and multiply by 1/10, and that's how you go from one element of the sequence to the next. So you have 1, 1/10, 100, 1,000, 1/10,000, etc. Right? The next is a 1/10 of the previous, and it's always the case in all these relations. What if your ratio is negative? Okay, well, then you will have an alternating sequence. I mean, here it was a special case of -1. If you had -2, then they will be alternating, and at the same time, their absolute value will grow. Well, you can so try to read off a formula. Also, this seems not so easy, right? But you try to fit some equations, and you will see. Okay, if you know, okay, so if you're told, okay, this is a geometric sequence, and tell me what the next one is, then you can see that it is, right? So this thing is 3 times that, and this thing is 3 times that, and this thing is 3 times that, etc. If you're not told, it might be a little hard at first, but anyway, you should just try. Just test, is this a geometric sequence, and see. So what are the conditions that make the sequence increasing? If you have a positive value and your ratio is greater than 1, so you multiply a positive value with something large, right? You grow. Or if a negative value is multiplied by, let's think of R as a half. So you have -10, and you multiply by half. It's -5, right? So from -10 you go to -5. From -5, -2.5, -1 and 1/4, etc. It's still an increasing sequence. It will go to 0 in the limit, but it's increasing. For decreasing, well, the positive start, and the ratio, that is a fraction, right? So from, let's take a equals 16, right, to half. So the next one is 8. Half of 8, 4, 2, 1, half, 1/4, etc., right? Or you have a negative number and you multiply it by something large, right? So then the negative numbers grow. Constant, well, if you start from 0, you always get a constant, right? It's going to be 0. Or if your ratio is 1, you just don't change. The sequence remains the same. There are funny cases, right? Like if R is 0 or if R is smaller than 0, you have alternating sequence. You don't have to remember this. You just know that whether it grows or doesn't, you know, if the ratio is fraction, then it will perform very differently, right? Behave very differently. Or if you start with a negative number, same rules act very differently. Arithmetic sequence. So similar, but for addition, right? So you start with a value, and rather than multiplying it by some constant, you add a constant. So this is an even simpler thing, right? Because the first element is d plus h0, so it's this, and the second is d plus h1, so it's this. So it's basically 2d plus a. Sorry, h3 is d plus h2. H2 is this, so you stick it in, and then you notice that d plus 2d, that's 3d, etc. So so you can read off the, hypothesize this formula, and indeed it's true for these cases, right? And it's not hard by induction to prove that it has to be true everywhere. That's the only closed formula that agrees with this base case and this recursive rule. Okay. So okay, let's go through some examples of arithmetic sequences. You start with something, you have some delta 2, right? It's strictly increasing, you add 2 every time. Or you add 1/10. Okay, well, this is strictly increasing as well now, right? Unlike the geometric sequence. What about if you add a negative number, right? Well, it will be decreasing, obviously, and let's say you're given some number and some sequence, and let's see if this is arithmetic. Well, what do you have to do to test? Is this, let's say that this is the previous one plus something. So what's that something? Well, it's the difference. That's 5. Is it the same difference now between h2 and h1? 9 and 14? Yes, it's also 5. What about 19 and 14? Yes, it's also 5. To test whether a sequence is an arithmetic one, just take differences of consecutive numbers, consecutive entries, and see if if all these differences are the same. Likewise, in the case of the geometric sequence, right? What you did to test this was you took the ratios, G1 divided by G2, G2 divided by G1, G3 divided by G2, and you saw whether all these ratios are the same, and they were 3 in this case. Okay, so these are your basic tests for recognition of arithmetic and geometric sequences. Now, these cases, whether they are equal or decreasing or increasing, this is even simpler in the case of arithmetic sequences. It all just depends on this d. So if it's positive, the sequence increases. Negative, it decreases. 0, it's constant. All right. Let's introduce summation. So if you have a sequence, okay, so it's a, well, it could be also for infinite, but let's say if infinite for finite, but let's say infinite sequence aj defined after some first index, let's say index 0. You can then this symbol, which is read sigma for sum, you sum this expression, which is a sequence value, for index j, which starts at starting index s and ends at some target index t. So this expression stands for the sum of aj for j equal s plus aj for the next j, which is s plus 1, plus aj for the next j, so this is implicitly a s plus 2, a s plus 3, and so forth, until j is equal to t, at which point you have a t, right? And that's the sum. So this is how you should read these expressions. It's a sum of consecutive values of the sequence, starting at some position and ending at some position. And you can have these functions, you can have a special symbol here, infinity. It's denoted with like a horizontal 8, right, like this. That would mean that this sequence goes infinitely. Except that in this class, like, we're not going to do this because, you know, our sequence is typically, so for this to be defined, it has to be that in a limit, this thing actually hits some, you know, it has a limit, right? And we will not have such sequences in this class. I don't believe, right? But you know, if you define this aj as say 1 over 2 to the j, then this thing will have a limit. All right, in infinity. Okay, so let's take an example. Define with the closed formula a sequence A as the kth element in the sequence is k squared. And implicitly, we don't mention where is the initial point, but let's say initial point is 0, right? So A0 is 0 square 0, A1 is 1 square 1, etc. Now you can evaluate what is the sum of elements of the sequence from 3rd to 6th. So this summation is A3 plus A4 plus A5 plus A6. There's a sum of consecutive squares, and if I evaluate it, I can, right, numerically. Now, you know, suppose that you define the kth element in the sequence using this closed formula. So it's 1 plus k squared. Then you can ask, okay, and now you say I want to evaluate the sum of elements in the sequence from the 3rd to the 6th. Okay, so it's again A3 plus A4 plus A5 plus A6, except that these are defined now by a different formula, which is this one. So this will be 4 squared plus 5 squared plus 6 squared plus 7 squared, right? Let's say that you have the same sequence of squares, basically, and you can use the summation formula to define another function, but it's a function on n. Let's look at this formula. It's a summation of elements in the sequence starting from the 3rd element, and then a 4th and 5th, and how far I go to an. So to this one. So if I arithmetically represent this, knowing how to read a k, right, is that this is 3 squared plus 4 squared plus 5 squared, all the way to n squared. And of course, if n is, for example, equal to 4, you know, this formula will not have these elements. I mean, it will end here. And n equal 3, it will end here. And n equal 5, it will end here, etc. Right? And of course, you can ask what's the closed for the type of formula for this, right? So is there a function which concisely represents this sum and which I can evaluate without explicitly performing, you know, this? In other words, is there a way to compute this that is not linear in n? So here's an example of a closed formula for this summation, the one I used all this time now, which is a summation of the sequences. Kth element sequence is k squared. So it's a sequence of squares. And here I have a summation for elements in sequence. So in other words, this equals the sum of first n squares. 1 plus 4 plus 3 square plus 5 square, 4 square, 5 square, all the way to n square. And here is a closed formula for it. So that sum always equals this expression. Now, this expression can be evaluated in a much faster way than in evaluating all of these if n is large, and then adding them, right? Because this is a polynomial of third degree, right? So, okay, how many operations you do, right? Like 1, 2, 3, 4, 5, right? So you do 5 pluses or moles, 1 division, and you're done. Constant number of arithmetic operations. Now, why is this true? You can ask. And one way is to basically apply induction. And the direct ways to show this will show that they basically are in the same form as induction in the end. But you can show this how? Well, it's the only formula that matches the base case. So it is 1 at n equal 1, right? You can verify 1 plus 2 plus 3, 1 times 2 times 3, that's 6 divided by 6, so it's 1. And then also matches the recursive relation with which you can define this. What is the recursive relation that defines the summation? I can define such a summation through a recursive formula, like how? Actually, I should have written this on slides or have some notebook to show you, but I will write it on the slide and post it. But if you can bear with me, the value of this summation at point n plus 1, or let's say at point n, is equal to the value of the same summation at one index less, so n minus 1, which express the sum of squares all the way to index n minus 1, plus what remains? N squared. So how does this expression differ between two consecutive values of n? If you imagine here was the summation from k equal 1 to n minus 1 k squared, what's the difference between this and that? The only difference is n squared. So I can define this as using a recursive rule. This is some function of n, let's call it sigma of n for summing. Sigma of n is sigma of n minus 1 plus n squared. So it's a recurrence relation. And using induction, you can show that this is the only formula that satisfies that recurrence relation and the base case. Okay. So here's a closed formula for the sum of terms in geometric sequence. Also very important. So as we said, the general formula for elements of the geometric sequence is r to the n times a. What about the sum of these? So what if I do a summation of GNs? Okay. Wait. What did I do? Oh, you know what? I messed up the slide. So I don't have the, sorry about that. I don't have, somehow don't have the sum of the terms in geometric sequence. I overlooked it. So I owe you a general formula for a sum of, for summations of these. And likewise, if I sum over HNs, what is the general formula for these, right? So, okay. sorry about this. These slides I overlooked. They don't make sense because I'm missing precisely what they promised, which is the sum, and what I should be telling you now. The formulas for summation of geometric sequence and summation of arithmetic sequence. The only thing I have remaining is the following formulas that can be helpful in evaluating summations. So look at the first one. So if you have to evaluate summations from of some sequence from, let's say, first to the nth element, well, you could split the job by evaluating it from first to some t index, which is between 1 and n, and then from t plus first to nth. And if you take an extreme case, and t is n minus 1, then this is the case I was talking about. If t is n minus 1, then this is a summation all the way to n minus first. And then what is here? If t is n minus 1, so t plus 1 is n. So I start from n and I end at n. So this summation will just simplify to just an. The only thing here will be an. And this is natural. The summation of any sequence at point n is the summation of the same sequence at point n minus 1 plus the nth element in the sequence, an. So that's one use of this formula. Another one, well, if somebody asks you, how about evaluating, let's say ak is a square, so it's k square. So this would be a sum of squares for this example, like that I used for a bunch of slides. But I don't start at the first one. I start at some index s for start and end at index t. Well, oh, I'm so sorry. There's a typo. This should be n. Okay. Because basically, if I have to look at what is the sum of values from index s to index n, then I can do sum all of them from 1 to n. Sorry, this is a typo. This should be n, right? And then subtract the values from first to s minus 1, because they don't participate here. But why would I do that? Because perhaps I have closed formula for the sum of the first n elements, right? These are the formulas, for example, I will have for geometric sequence, sum of the first n elements in the geometric sequence, sum of the first n elements in the arithmetic sequence, etc., right? Sum of the first n squares, sum of the first n integers, sum of the first n cubes, etc. So I can plug in this formula here. Again, this is n. This thing should be n. And plug the same formula here and then subtract, right? So that's why this is useful. Another thing is a change of variable, change of index. So you, regardless of the start and end of the summation, perhaps your expression here is expressed in some way. You can read it off as some sequence that you know that is somehow an easy sequence to think of, but it's indexed in an uncomfortable way. It's indexed not at these indices here, but that this index shifted by some delta. So look, let's do a change of variable. Let's call k plus di. And if k starts from s, then I starts from s plus d, right? Because define I to be k plus d, right? So the first I is s plus d. And what's the last I? Since last k is n, and I is n plus d. Oh, I'm sorry. Here is the same typo. This is n plus d. So here is n, and here is n. Yeah.
A quick question, if you don't mind, real quickly. For the second one, so summation of k, this way right there. So yeah, right where the mouse is. So then k is equal to 1 till k to 2t, right?
No,
So then
n.
n? Okay, yeah, because n, and then you're going to be subtracting k minus 1 till, okay, s minus 1.
Okay. All right. Sorry, this is n. And here is also n. So we sum to n plus d, from s plus d to n plus d. And this is, so I use this intermediate variable I, but I can, look, I can change the variable, right? So this is a free variable here. It's an index that goes from some start to some end, and I use it to index this a sequence element. I can use a different index. For example, the original one, k, right? It's just the name of the variable designating the index. So these two expressions, and again, I'm sorry, but this should be n, okay? These two expressions are the same, right? They're just shifted, the index gets shifted. Rather than use the shift here, I basically migrate that shift into here. All right. And now I simplify my expression, right? Because if this is some complex function of the index, then perhaps it's much easier to think of, to simplify the index and just think of the beginning and end as differently. Okay. That's all I have. So I will fix these typos, and I will also add the explicit geometric summation and summation of geometric sequence and summation of arithmetic sequence formulas to this slide. Do you have any other questions? So we open for questions.
Is test 4 still, or is the first test still during week 4?
Yes.
Okay, thank you.
Sure.
You know exactly which day is test 4?
Yes, it's on our website. It's on
Oh,
admin
okay.
slides.
Under the
I forget
slide?
the date.
Okay.
It's Thursday, week 4.
Okay.
Well, yeah, maybe I should like bring them out and put them in bold font on, you know, yeah. Maybe I would do that.
April 23rd, right?
I don't know. You check. I don't want to tell you because like I will have to check my own slides, right? So I think that sounds about right.
Yeah, it's a Thursday, 23rd of April.
Okay. It's 2 weeks from now. Yeah, because we are in week 2 now. So it's exactly 2 weeks from now. Is it going to be during lecture time? Yes.
A quick question about the summations. Are we going to have like multiple summations in one? Like, you know, like you have a multivariable summation?
I don't know. Multivariable summation. And you have to give me an example. You will see what we have. I'm not sure what you mean by multivariable summation. No, like all my summations are. Summation is always for a single sequence. There is some sequence, and you sum over elements of that sequence. In that sense, you always sum for a fixed sequence, for just one sequence. The date of the final, there is no final. Somebody asks. I'm reading off questions on the chat, but if you have questions, ask them. Oh, somebody does ask, do we need to do all the Zybook exercises? Yes. They ask when, whenever you want.
Do we have we already have covered recursion here, right?
Well, one form of recursion. Recursion
Okay.
is something that is going to come again and again, and in the next 2 weeks for sure. But recurrence relations are a form of recursion, and that's why there is a recursive algorithm is a good. I mean, they are actually recursive algorithms. They're recursive algorithms that compute a function. So that's the recursive relation. The yeah, that's the form of recursion that we have seen so far.
Okay, so my other question was for multivariable summation is I have an example. Like you have a summation of like j is equal to 0 to 1. And then inside that summation, you have I is equal to 1 till 2. And then the formula is j minus I minus 1.
No, I cannot go so quickly. Like write this on a piazza using the formula editor, and then it's clear what you mean. So
Okay.
I will respond. Do we have somebody asked, do we have to memorize these formulas? Yeah, like you have to know what an arithmetic sequence is, what a geometric sequence is, what is the sum of geometric sequence, sum of arithmetic sequence, and the sum of squares and the sum of integers. I think these are the ones that you should remember. I mean, maybe there is one more that I will ask you to remember, but these are the ones for sure.
Can you go over how to change the variables in the bottom again? How you did that? Like
yeah. So this is just sorry because there's this typo here that this should be n, but it's just that I'm defining I to be k plus d. So because I have this uncomfortable index right here, right? So I would prefer this to be AI because it's just going to be easier for me, because let's say this is some complex formula. So I don't want to think of this in terms of k plus d all the time. I want to think of them in terms of some single variable. Let's call it I. So in other words, I call k plus di. And if I do so, and as then how can I rewrite this in terms of summing this sequence for this index? But I just have to start at some point and end at some point for this to be true. So if I basically start, what is my start sequence? It's for k equal s, this is s plus d. And look, I'm gonna hit the same thing. If I call this I, then I start from s plus d. Okay, let's verify that I did it correctly at the end, which I didn't because there's a typo. But so what's the last guy? A of the last k, so that's n. So it's A at index n plus d. So if my index is I, the last index should be n plus d. Okay, and minus the typo, it is. Right, so that's why I did this.
Thank you.
Yeah. And you know, this I explicitly have this intermediate variable I, but you can jump from here to here straight away, right? Because this is it's just a variable change. Yeah, it's a renaming of the variable. In this expression, it's the same as this expression, but with this variable it being effectively this one plus d. Yeah. But I mean, seeing this is easier. When the explicitly called a different variable, it's easier. It's just that this equation is also true. Because it's like, you know, this is a piece of code that evaluates something, right? And k is here just an index that goes from sum first and looks up and evaluates and sums, and then it increments and then looks up and sums and increments and so forth. So it's a free variable. It's a, you can think of it as a for loop. For k equal s plus d to g plus d, sum ak. So start with some initial value 0, and just add AK. Or you can think of this code here. For I equal, initialize the sum at 0 and do a following loop. For I equal S plus D to T plus D, add to the whatever sum you have, AI. I is a free variable here. It's just an index. It's just the name of the variable. And here K was the name of the same variable. So it doesn't matter what you call them. You can call them I, you can call them K, right? Somebody asked if I'm going to fix the typos. Yes, at least those that I notice. And if you see some other typos, let me know. By the way, if I post the slides and somebody sees a typo, post it on Piazza. Like, there's a typo on this page, so I correct it. The only typos, I mean, the ones I remember are these, right? The ends. If somebody remembers some previous one, tell me. Okay. Any more questions? Okay. So see you next Tuesday, and start on homework 2. Use office hours, and come to discussions on Monday. And hope everybody is well. Bye, everyone.